Elias holds a Master of Science with distinction in quantum fields and fundamental forces, and a PhD in theoretical and mathematical physics, both from the Imperial College of the University of London. He has published papers on category theoretic methods in quantum physics and complex systems theories, modern differential geometry and topology, and many other topics in the foundations of physics and mathematics. He is also the author of 3 books on this subject, and he is, as I was saying, a lecturer here, a teaching professor of mathematical thinking at TU Vienna, but he is also a research professor in theoretical and mathematical physics at the Institute of Mathematics at the University of Athens, and we are very happy to have you for this lecture. Thank you, Elias.
So thank you very much for the introduction. It's really a pleasure to be with friends. And the subject of my talk is going to be about the static tripod. So I would like to start with this very simple idea of what a tripod is, because I think that very deep things are hidden in very simple notions. So when we think about a tripod, basically something which has 3 legs. So if we think of it on the plane, in space, what we have is the iconography of a triangle. And without loss of generality, we can consider that this triangle is an orthogonal triangle. In this way, I would like to connect with the Pythagorean theorem that we talked so much yesterday. So the idea is that if you see it in space, you have an orthogonal triangle, and you have the usual thing which is called the incommensurability of the side with a diagonal. But if you see the same thing in terms of areas, then areas become commensurable in space. So the area here equals the sum of these 2 areas. This is like a frozen picture of things in space. Now I would like to invite you to think how the whole thing looks in time. And what I mean by time here is just you start rotating this triangle, okay, at this point. So what you observe here is that the diagonal makes this big circle around, okay? This side A, okay, makes the small circle. And there is, in between, a ring region, okay, such that from the Pythagorean theorem, the area which is included here plus the area of this ring equals the area in the big circle which is made by the diagonal. So in time, what the Pythagorean theorem says is that the area of this ring equals the area of this circular disk, okay? Which is a highly non-trivial result, okay? How a ring can have the same area like a circular disk. Now you can use the same way of thinking in reverse, and you can give the simplest visual proof of the Pythagorean theorem, because you see that this B here, okay, if it starts rotating, it is sliding over the inner circle. But if something is sliding along without rotating, it does not enclose any area. So in this way, you get, inversely, the simplest possible proof of the Pythagorean theorem. Okay? Somebody that can, by seeing at it, can understand it immediately. Now, what this thing says is that the circular ring, this type of thing here, is what the ancients were calling a gnomon. A gnomon is something which, if it is adjoined to some form, it gives rise to a similar form. Okay? So this is the way to go from the small to the big, and from the big to the small, by adding adjoining gnomons. And as I said, you consider the rotation here, but you consider the rotation on the other points, like here or here. And then you see that actually you have 3 gnomons. So all the sides of the orthogonal triangle, they function as gnomons. So let's try now to explore what is behind this thing if we abstract from the metrical point of view. So area is a metrical attribute. Let's try to see what it says topologically about the relations between three rings, because as you see, the gnomon is the ring. So if you try to consider now three rings in three-dimensional space, and I would like to invite you to think how these three rings can be linked. The most usual answer you get is this chain-like linking. Okay, we think, because we're immersed in thinking from a spatial point of view, that the rings are linked together in the form of a chain. But what is behind the Pythagorean theorem is that any of the sides of the orthogonal triangle can function as a gnomon for the whole thing. What this says is that if you remove one of the sides, then the whole thing falls apart. And this is what gives substance to the domain of time. So here in this linking configuration of the three rings, if you imagine that you start to pull apart the two of them, you see that the third one is getting intertwined between the other two. Now, what this whole thing means, and why this is relevant for conceptualizing the notion of a tripod in time. If you consider that these two rings, A and B, they are moved in opposite sides in the universe, so the distance doesn't play any role. The third one will still connect them. So this is what we mean by a topological property and not a metrical property. Because you would think that it is the distance between them which keeps these things apart, like in the chain-like linking. Here we do not have this phenomenon. Okay? What we have is that this configuration here of linking is independent of the distance. So it doesn't matter how far you pull them apart. The third one, we will still connect them. And this is a property which gets out, which invites us to leave the geometrical way, the space way of thinking about the global linking of things. Okay? So this is the entrance to the topological domain, and what is behind it is what we call the harmonic domain. Here, you can see a kind of three-dimensional rendering of the same thing. It's what I call a tripod, and the semantics of it is a kind of diachronic, it means through time, temporal bond. So this is not a link in space, but it is a link in time. So it functions as a bond in the temporal domain. What you see about these three rings is that, for example, if you take the green ring, you see that it is completely inside the red ring. And the red ring is completely inside the black ring, which is in turn completely inside the green ring. This is the essence of a non-chain-like linking. It's a totally self-referential relation. Okay? And it gives us a hint of what a kind of temporal bond would be like, and why the ancient people were thinking about a tripod as a bond. So here is a cross-section of this linking. Now, why I have put it here? Because this cross-section here is the cross-section of the tripod, which you can find in Delphi. Okay? This is the cross-section of a tripod which was on the top of the oracle. Okay? And the whole idea is that the sender is something that is not explicable. It's the kind of primordial obstacle. And this is what has to be resolved. And it is resolved through this intertwined type of circulation. Now we see that this idea of a static tripod basically refers to a kind of threefold stable communication relation which aims to embrace the obstacle which is in the middle. And you see that we need three entities to function like this, and out of this we make a trivium. But we cannot have access to a trivium, we cannot analyze it, we cannot mathematize it immediately. We have to make a quantrivium, so we have to go to a domain of simultaneity in order to see how this scheme works, because it refers to a kind of communication relation. So the idea is, and this is the mathematical model that I have been working with, this model of what I call natural communication, and mathematically is expressed as a principle of conjugation of obstacle-laden domains. Very simple. You consider different levels or domains. And at the top domain, there is something which is an obstacle. It means that if you walk towards it, you will break your head on a wall. So the idea is that you have to devise some bridges which will get you to another level through which you can move through this different domain here, okay, which is not obstructed by the obstacle. And then, of course, you are not finished because you have to go here. So what you have to do is to follow a kind of inverse bridge. And like this, you are able to embrace the obstacle here. This is a process which is called metaphora in Greek. We use in English the word metaphor, but the linguistic meaning of metaphor is not as rich of what metaphora is about. So metaphora involves an encoding bridge and a decoding bridge, okay? And like this, you can embrace the obstacle here through a communicational procedure. So you make this level W with this level T here to communicate to each other through two inverse bridges, where this is the encoding bridge and this is the decoding bridge of the scheme. What is the lower level? How we will think about the lower level? The lower level, which is not obstructed by the obstacle, has the function of a kind which is called partition spectrum. Partition spectrum means that you have distinct blocks which you can think of in terms of colors. So, for example, light frequencies, okay? And these are what? These are mutually exclusive, but they are jointly exhaustive. In this way, they form the observable spectrum of the partition. So, in this way, the intractable problem that you have on the upper domain, okay, can be resolved in terms of colors. Okay? And this is the domain now that in mathematics we call the domain of spectral geometry. So spectral geometry is a kind of color geometry through which you can access another level that you cannot see. But this level, maybe you can hear, okay? And the problem is how you will connect these two levels. Okay, here is three algebraic properties, but it's better to explain them. It doesn't go back, right? Okay. So what are the three properties? The first property is that this process, which functions as a key, okay, and it's a kind of motivic key because it applies in the same way to every situation like a motif, can be extended in depth, so you can have more than one levels, okay, in this procedure. You can have levels and problems which share the same bridges, so you can consider the product of them. And the third is the inversion property. So if you have the W being conjugate to T through these bridges, you can consider now the T here as being conjugate to the initial W through the inverse bridges. Okay? So this configuration has a very interesting symmetry that we are going to exploit. Okay, but doesn't move. Maybe. No, no, it's okay. Okay, good. So let's try now to make sense of this static tripod in terms of this linking theory that I try to present to you. And I don't want to be abstract, so I want to apply it on the relation between mathematics, architectonics, and philosophy. So I would like to think of them as legs in time of a tripod. So they form a type of link of the form that I presented you before. Now, why this thing works is that if you consider an iteration of a tripod, so a tripod of a tripod is again a tripod. Okay? So with this property, you can relate three tripods together. What this means now, practically, is that you are able to transfer isomorphically structural elements from mathematics to architectonics and to philosophy, or the other way around. So if you choose any two of them, the third one will be the third ring, which will give bridges to connect the other two. So if you consider in mathematics the relation between, what is the tripod in mathematics? I consider the relation between harmonics and the relation between geometry. I will explain briefly what I mean by harmonics. Most of you, I'm sure you know what geometry is. What are the bridges? The bridges are made by arithmetic and topological scales. They need to have both because this link is a topological link. This means that the arithmetic bridges have to be of a transcendental nature. And with this, we go to the domain of the imaginary numbers. You will see that these here bridges are the exponential and the logarithmic function. But this cannot be thought purely on the arithmetical domain. We need to take into account topological aspects. The isomorphic transfer of structure here in architectonics goes on the relation between design and architecture, where design fits with the domain of harmonics and architecture with the domain of geometry. And the bridges are what we call weaving, like what you see in this building here. This is a weaving pattern. And on the topological side, so we can think the weaving on the arithmetic side, and on the topological side, we see the notion of a column. So we have to make sense from this point of view what really a column is. Okay? Not as a built thing, but how first people thought about the notion of a column. On the domain of philosophy, now, we have what we call the global to local relation, But you see, we cannot consider both global and local in the domain of geometry. We are out of the domain of space. So the global has to be related with the domain of harmonics and the domain of design. And the local fits with the domain of architecture and the domain of geometry. Now, the bridges is what in philosophy is called a kind of canon. A canon between the one and the many, or a canon between the part and the whole. And, for example, in Platonic philosophy or Aristotle, you have this continuous problem of thinking about the relation of the one with the many. So let me briefly review what I mean by harmonics, because this is the main thread of where I want to base my analysis of the global. So harmonics, first of all, where it comes from. The Greek word for it is harmonia. Harmonia is how to fit together things compatibly, not in space, but in time, within precise bounds. Okay? And the model of this is the model of the monochord. Okay? How Pythagoras started to experiment with a vibrating string and how he made a scale out of it. A vibrating string is very different from a line, a geometric line in space. So the way to understand this now from a physical point of view, which is very modern because this is the essence also of the quantum way of thinking this domain of harmonics, is this idea of a standing wave or a stationary wave. Now, what is a standing wave and why we call it standing? Because everybody thinks about waves as entities which travel in space-time. But the standing wave doesn't have to do anything about space because you have the bounds. So the string is always bounded. The space is fixed. So the whole behavior refers to time and the resolution of time. The resolution of time for every single moment is possible due to the harmonic frequencies which are developed by the monochord. So in this way, you have an extra dimension of depth which cannot be thought geometrically in space. The frequency domain, okay, it's what we use now for what we call quantum technology. Everything is based on the domain of frequencies. And the domain of frequencies is based on this simple idea of resonance. And the idea of a resonance is independent of metrical distance. So it reminds now of this kind of linking together that I showed you in the beginning, because metrical distance doesn't play any role. The harmonic frequencies here, they appear always in integer numbers. So they have a quantum behavior. They are the basic quanta in the world of frequencies, so in the harmonic domain. And if we want to think now about the relation, this very simple looking relation between the ear and the eye, this is a highly non-trivial thing. We have to be able to build bridges between the ear and the eye. And the bridges here, they have to take into account the domain of the frequencies. This is what I will try to explicate through what I call the complex analytic functions, the exponential function and the logarithmic function. They are called transcendental functions in mathematics. And the role is how you transform from this domain and back. You always need two bridges. Out of this now, for example, the Pythagoreans made the scale, the harmonic scale. Okay, it's how you make music. Where the harmonic scale now, it has the pure ratios of pure frequencies. But if you transform this scale into geometry, in music, you are in the domain of the equal temperament. So you need modulation, And you make, in order to make a geometric scale, which is called the chromatic scale, you need, to make modulation. You do not have an immediate translation from this domain to this domain. Let's see now in architecture how this scheme is transferred isomorphically. You know about this type of patterns. These are called meanders. What were the meandering patterns? Can you see of them as purely geometrically? No. You see that they have some repetition and they come in a kind of different harmonics. The first thing you observe is that this harmonics they come in quanta, so you can think of them as different quanta, of frequencies. And they also have another property, which is the property of chirality. What we mean by chirality is that this type of patterns have an orientation, and there are two possible orientations. Now, if you imagine these two orientations being glued together, what you get is a labyrinth. A very old symbol, even from the Minoan times, the story of the labyrinth. So this thing now is not in geometry. This is in the domain of harmonics. And the problem is how we move from this domain to the geometric domain. And what the ancient people thought of this kind of bridge is given by this pattern here, which you will recognize that this is the spider's web. In Greek, the spider's web is called arachne. It has the same root like harmonia, like arithmos, like archi. All of these words, like the word art now, or articulation, they come from the domain of harmonics, not the domain of geometry. So we need bridges to be possible to go from here to here. And very simply, in this polar grid, you can see the bridges, you can think of them as the Ariadne's thread, and the degrees of freedom of this thread is to move either on the radial direction or to move on the angular direction, or to have a combination of these two things. The combination of these two things gives rise to this kind of paths, and this path is what defines geometrically what we call the logarithmic spiral. So the logarithm comes from the combination of the radial and the angular. You see that it's like moving diagonally. And it gives the way now to move unobstructively in this polar grid as a kind of representation, or not representation, it's in time, so it is representing, not representation in space, but presenting on its moment. So you move from harmonic frequencies to harmonic frequencies, and you can go out following this logarithmic spiral, like how the spider makes the web, and then you can move back through the radial direction. And if you do this, then you have another type of spiral, which is called Archimedean spiral. And like this, you make a round trip. And this is exactly how the spider makes the web. And that's why the spiral is called with a name that originates from the domain of harmonia. Now, in modern terms, we have precise mathematical ways to describe these things now. So they are not somehow ideal, or this is how quantum technology works, with these bridges. This circle here belongs to what we call the complex domain, the domain of the imaginary numbers, not the real numbers. The problem with this domain, like with every domain of frequency, is that you have a property which is called multiple connectivity. See, very simply what this means is that if you are here, you do not know if you are on the first turn, or on the second, or on the third, and so on. So the angle is a multi-valued thing. So this gives a multiple connectivity to the whole thing. So in order to be able to transform this harmonic ring here to the geometric domain, you have to be able to unfold it. And the unfolding is in terms of windings, which corresponds to different frequencies in the domain of countable frequencies, okay? Different quanta. So this now is a domain where the harmonic circle has the behavior of branching. So it creates different branches here. So each frequency corresponds to a different branch. And how would you get back? So if here is branching, the other direction is multiplexing. This is the behavior of multiplexing. So you put many things, all the different branches, you unify them, not geometrically, but on the harmonic domain. And if you want to see now how they look like on a two-dimensional projection, the helices here, they correspond to what they call logarithmic lines. So on the logarithmic scale, the helices becomes straight lines. And you see that this region here of the helicoid, because this branching is a helicoid, corresponds to this domain here. So in 2 dimensions, we have this correspondence, and you see that the circle and all the circles become vertical lines, whereas the radial directions become horizontal lines. So the complex exponential and the complex logarithm functions are the bridges that we are looking for in order to transform from the harmonic domain to the geometric way, and the other way back. Now, why these bridges are very good? Because they have a property which is called a conformal property. What is conformal? It means that they preserve oriented angles. So it is the angle, it's the preservation of the angle which makes possible the communication between the harmonic and the geometric domain. And you see that with an angle which is preserved conformally, you can go from the micro level to the macroscopic and to the megascopic level. So it encodes a concept of similarity which is not only geometric, but is able to bridge together harmonic and geometric domain. Let's try to see now how this scheme applies in the relation between design and architecture. So when we think about design, the design refers to the global, and somehow the global is imposed or envisioned. It's a kind of vision that you have about the global. The local parts are organized in a way so as to comply or to fulfill this global vision. The constraint of design is that you have a restriction of the local part by the global, and at the same time, you have a restriction or a contraction of the global to the local without degenerating the global. Okay? Because if you degenerated it, then the design would not be proper. Now, in architecture, we have exactly the inverse type of relationships. So, in architecture, you start always with the local parts, which are selected always as atomic elements, and are organized in a way to open up a new space. So you have many local elements, and your problem is how to make assemblies out of them in order to open up space. So you do not consider it in space, but you try to open up space through the connection of these things. The constraint of architecture is that you have the extension of the local part by joining it compatibly with other local parts toward reaching the global. So you see that design and architecture work inversely. I continue with this frame of thinking, and I consider design again, and I will use a concept that I credited to Ludger, which pointed out to me that in design, basically, the local parts are passive, whereas it's the global which is active. So we have this active-passive distinction. In architecture, the local parts are the active elements, and the global is a passive thing. But through these bridges that I showed you before, you can achieve a kind of bidirectional communication relation between design and architecture. So very briefly, design, that's my argument that design descends from the domain of harmonics. Architecture descends from the domain of geometry. And the bridges, in order to make sense of this communication relation, are what we call in mathematics the basic transcendental functions, which is the complex exponential and complex logarithm functions, which, as I said, they are conformal. They are based on the preservation of angle. Here is a topological rendering of the whole thing through the notion which is called the sheaf. I will be very brief here. I don't want to go to technical details, but again, you see how you can think of it as kind of belonging to the harmonic domain, and here how it unfolds, okay, and gives always rise to this type of branching behavior in the geometric domain. So the multiple connectivity that you have here is resolved through branching, and you have a simply connected geometric space. So this is of an architectural nature, this is of a harmonic nature. And the compatibility now, what I called initially the partition spectrum, you remember the partition spectrum is in terms of colors. How I go from the local to the global, so you consider different disks, for example, and they are overlapping spatially, and then you can join them together, and you can extend from every local part to a bigger local part until you reach the global. Okay, this is how it works in the domain of complex analysis and synthesis, of course. So the general figure that I want you to keep in mind is this idea of a helicoid, which is the universal covering or unfolding space, okay, of the harmonic circle, is what you do in geometry, and the different levels of this helicoid are the different frequencies. I have to move faster. So I come again on the relation between design and architecture, and I make the claim that if we want to think in causal terms, then basically design is characterized by what I would call teleonomy, or what the ancients call entelechia. So we have the notion that a final cause, if we think of them in linear terms, this is forbidden. But if you think of entelechia in harmonic terms, makes perfect sense, because the harmonics is exactly what you expect out of resonance. So the design is characterized, and this is why design can work, is designed on the harmonic frequencies. Okay? So it's characterized by teleonomy and entelechia. Architecture is characterized by elementarity and efficient causality. So I want to pursue in more detail now the relation between design and architecture. And if I want to see now in architecture how this whole thing applied in the case of a column, that's my final purpose. I don't know if I will have time. If you give me another 5 minutes, maybe I will be able to compress. So in architecture, we have the constraints of the three-dimensional space. This means what? that in architecture, what you can do is you can rotate things and you can translate them. But if you combine them together, translation and rotation, what you get is a helical or a screw motion. So we have to think of this combination. How this now is generated from the domain of harmonics. I will be very brief. The whole idea to generate geometry out of the harmonic circle is what is called in mathematics the roots of unity. So you think the circle, the harmonic circle, as the whole, as the global, and the different parts, they are roots. So we're talking not about a division in space, but we talk about cyclotomy. Okay? Cyclotomy is not the same like a division in space, because through cyclotomy, you see that this is the second roots. Here you go to the third roots, okay, which is a cube root, and you generate a triangle. And if you go on, you generate a square, and so on. So you get geometry out of the roots of the unity. This is how you go from the global to the local. And this is the example of the 8 roots of unity. Okay, so you have 8 different roots, which makes the cyclotomy. And if you connect them together, they give an octagon. Now, there are some roots which are called primitive. The primitive roots are what we call the prime numbers, basically. So the role of the primes, considered as atomic elements, they are played by the primitive roots. And in the case of the 8th roots of unity, you see that there are 4 roots which are primitive and 4 roots which are not primitive. So I can assign the 4 roots to one wave and the other 4 roots to the mirror image of this wave so as to make a resonance, which is a standing wave of this configuration. Okay, let's see how how you can make architecture with this, how you can build a column, because that's my point. So we said that the active local parts can be joined together by geometric transformations. And we model the active local parts by the geometric form of the graphs of these roots, which are basically polygons. You see that if you consider the 8 roots of unity, what you get is a superposition of 2 squares. These 2 squares now, they come from rotation, and they differ by a half period. So this now is what, in the harmonic domain, represents a kind of, the kind of unfolding which comes from the 8th roots of unity. But this comes actually from a standing wave, because you have this square here, and you have this square here. So you can consider it as a kind of geometric template to make a column. So how you make a column? In this way. So the geometric template, I break the octagon in 2 squares like this, which form a star. Okay, an 8 star. These edges here, the sharp edges, can be smoothened, so you get this kind of thing. Okay, this is going to be the basis of a column. On the second level is that you consider the double helicoidal motion of this template. So this template, okay, is a helicoid which can unfold either in this orientation or in the other orientation. These 2 orientations together, what they give rise to a weaving pattern, okay? And you see that where they intersect is the harmonic frequencies. So you have a way in the geometric domain to represent the harmonics. So the weaving works because it respects the harmonics of the harmonic domain. And what you do next you treat a bounded column as a kind of branch of the global. So each column, you can think of it as a branch of the global. And the idea is to join branches together. Now, if I start joining branches together, what I get is a tree. Okay? Because why? At every joining, what you do is you double the numbers of the roots. This means that the partition spectrum here becomes more and more rich. You join together more branches, you reach this level. And I finish with the last demonstration. We know from the work of Archimedes now that what we need in order to approximate the circle is polygons of 96 sides. So how do you make a column? There are two ways. The first way is to implement, through this resolution, striations on the columns. So the columns in the ancient orders, they are not cylinders. They have striations. And the fact that they have striations means that they descend from the harmonic domain. Otherwise, they would be simple cylinders. That's the first way. And the second way is that you can think of a tree now as a column. Why? Because this branch here, okay, which is a logarithm, basically, if you join it with this, the number of the roots of unity here, it doubles. So in every joining together, you double again the roots until you reach to the best approximation of the circle. You can very easily reach with a tree the 96 polygon of 96 sides. That offers the best approximation to the circle. So in geometry, is the tree, which is really a column, and makes the communication between the harmonic domain and the geometric domain feasible. Okay, I finish here. Thank you.
Thank you very much, Elias, and I think all three lectures were really nicely shedding different lights on this question of the global. Questions, comments? We have 10, 15 minutes to discuss more.
I mean, I have what is just a very naive question about the phrase natural communication and these bridges that you're thinking. Mm-hmm. I mean, it's almost a very stupid question, but it's about the use of the word communication there. Like, what is it a metaphor? Is it a structure? Is it, when you're saying natural communication, how are we to think? What is the communication that's happening there? Is it within, what dimension is that communication?
Very simple. How, for example, your ear communicates with your eye.
Okay.
So what happens in your brain when you want signals which come from the acoustic domain, okay, to talk together and to coordinate with signals which comes from your eye, from the domain of light. There is not an immediate process. You need a transcription. You need bridges. This is what I mean by bridges. And these bridges now, we have discovered that they are transcendental bridges. Okay? They cannot be expressed in the real domain. We have to go to the imaginary domain, which we know how it works mathematically. And the exponential functions and the logarithm, they belong to this domain. And through this now, through going to the transcendental, we can make sense of this very simple communication relation between the ear and the eye. And I think this is really something which is amazing, at least for me.
Thank you. I have so many questions really to get to grips with this. But I suppose really, I'm still relating it to a quantum philosophy that as I have understood it so far. And to me, there is perhaps something very useful that Bachelard said in The New Scientific Spirit, where he was talking about the mathematical object. And he said, we can say to the mathematical object, tell me how you are transformed, and I will tell you what you are. Mm-hmm. And it seems to me that you are operating very much on that territory. It's not that there is a pre-given mathematical object, because we can see a picture of something, say a picture of a square, yeah. But we might be told that this is a projection of a cube onto a Euclidean 2-space. But then again, the original cube might be a projection of a hypercube onto a 3-space. So we ask always, what we have to ask is how of the mathematical object is, how are you transformed? And because that's true, we can't simply say that of any given mathematical object that it is something, that we have something in front of us. What we have to ask is, how are we to transform this, or what are the processes through which it may be transformed? Mm-hmm. And again, because that's true, we almost get to something like, you may not resist this idea, we are almost at the point where we could say there's a kind of transcendental synesthesia in play in what you're saying. Because the visual has to be related to the aural, but it's not in any straightforward sense. It's not like a visual perception is related to an aural perception. We are above that. We're above the number line, and we're in a transcendental space where that's true. So there you go. There's a kind of phrase that I wonder if you like it or don't like it. Transcendental synesthesia.
Yes, because synesthesia somehow it is bringing together or joining different aestheses, which is what I'm talking about the ear and the eye, for example. And in order to make them communicate, because this is what happens in our brain. It's a kind of communication, but for this you need transcriptions. It's not immediate, so it's extremely complicated. And the most interesting thing is that this happens through the transcendental. So you need, in order to make sense of it, we need to go to the complex domain. We need to use the imaginary numbers, the imaginary circle. So we go to the domain of harmonics. This is the domain of harmonics, a domain of quantization, basically. So we have this classical to quantum transition in order to be able now to make a model of how our ear and the eye, they work together, so they have some synergy. Because synesthesia is the first part of the whole thing. It's one bridge. You need to make the inversion of it. Okay, you need the synergy in order to be able to function as a unity. And that's a way, what I mean, this kind of many to one or local to global relation, it works.
And of course I like, and I know these stories, but a short comment. I think with communication, you have always a sensor and actuator, receiver and sender, and so on. Therefore, you can't do it with your senses. I think it's not the eye and the ear; it's the talking and the looking. So you need an active and a passive part.
Yeah. That's the inversion, the synergy that I'm talking about.
You are in communication.
Yes, because you have the aesthesis, the sense, but then you need to make through speaking and looking. Exactly. Yes. So that's the synergy. It's the inversion of the whole thing.
So then my hypothesis is that, just as a remark, that our Western culture is just as a primacy of the active part is in harmonics, and the passive, the sensory is with the eyes. It's in the geometric realm. That with in Asia, in the Chinese part, it's just the other way around. Yes. So that the primary sense is the ear, and the primary active part is in geometry, which is the hand and the craftsmanship. It's just
it's the other way around, exactly. It's
yes,
reversal.
This would be very interesting to research on.
Yes. Yeah, I totally agree with this, and I think we have talked a lot about this.
I would like to come back also to your question and to relate it to your talk yesterday with Descartes. So as I understand in Descartes, the key of saying natural geometry, like Kepler did as well, was to say that geometry is of the same nature like the nature that it can describe. And as I understand you, this is your turn as well. So the nature that your communication with the bridges can describe is of the same nature like the communication itself. Yeah?
Yes.
So there is that's why there is this constitutive self-referentiality at work in it. But then the question would be is, so in Descartes, what clarified this relation for me very much is that he says, I make light the central paradigm within which he wants a physics of light, which I treat like a metaphysical principle in order to get this plenum space. But then he says at the same time, but the true nature of light, about this I can say nothing. Yeah? So he constructs a natural way of thinking naturally about the nature of light, which is not the true. So he keeps the two apart. And you are talking about the transcendental. Is it a similar move, like with Descartes, that you are thinking, or?
Yeah, and I'm emphasizing it, that this type of communication is of a transcendental nature. And, but for me, this other level, it belongs to the domain of harmonics, and the domain of what we call now quantum mechanics, basically. Where you are not in the domain of space and time, but you are in the domain of time and frequency. And
so what would it be for you? Would it be a magma? A kind of
yes, for me it's a kind of magma,
so
exactly,
kind of
yes.
Like Descartes treats light, and then the true nature of light, you have like material, so quantum physical materiality, and then a similar split with a magma.
Yes, yes. Which can be water, yes.
I think that unless there is one more question, if there are no more questions, I suggest that we take a break for lunch. Thank you very much, Elias. Thank you to our three speakers.